Well, welcome to the third and final of our live streams concerning the rendering controls of the Mandelbulb 3D software. Now, if you recall in our first two live screens, the last two Sundays or so, we were talking about the process of ray marching. Now, what I'd like to do in this live stream, we're going to see if we can cover a couple important calculation settings pertaining to rendering. Now, if we just take a look at the calculations tab right in here, we were talking about the DE stop. All right, we talked about the ray step multiplier in the previous live streams. What I want to do right now in this stream is talk about the vary DE stop on FOV. I want to talk about the step count for binary search, smooth normals, and normals on DE, first step random, and ray step sub DE stop. Now, those are important settings for a good quality render, as I will demonstrate. Okay? Now, let's just do a real quick review here of this whole idea of ray marching. Okay? Now, if we just we go on over to our blackboard here, as you recall, I got a camera. All right, and mathematically we're going to shoot out a ray, and eventually we're probably going to hit an object, a fractal object. Now, as you know, a Mandelbulb fractal is an object. It's a structure that has been mathematically created and is in space, 3D space. What the ray marching system needs to do is to locate where the surfaces are of the fractal. Now, this is going to happen for every pixel. Okay, every pixel is going to have a ray shot out from the perspective of the camera, all the way out to where it hits a fractal object. And if it doesn't hit, say for instance this way, then it goes off into space and eventually comes to a point where it says, I'm not finding anything, there's no object there in the scene. Okay? All right, so what we want to do here is just recap real brief. Now, what'll happen is that the ray marching architecture, the system, will shoot out a ray and will say, is there a hit here at this particular step? Now, that step is determined by, I should say, the size of the step, the distance out from the camera. Okay, the size of the step is determined mathematically by a couple different variables. All right, so that step is what the Mandelbulb rendering math feels that is a safe step. And then it'll make another step. Is there a hit there? No. Makes another step. All right, is there a hit there? No. Eventually, it's going to come to a point, if there's a fractal object in the path of the ray, eventually it's going to come to a point where it says, all right, I'm very close to hitting this surface. And this is the area that will hit the surface. Now, there's a couple elements that we're going to talk about in this live stream that pertain to right in this area right here. Just as the ray mathematically gets to a point where it is about to or has hit the fractal surface, that's the controls that we'll talk about today. Okay? But this is an overview. The ray marching system in the Mandelbulb design will send out a ray, and it'll step along the ray, and it'll say, do I have a hit? No. Hit? No. Hit? No. Hit? No. I'm coming close to the surface. Now, all right, so let's now take us into these other controls pertaining to the rendering system of Mandelbulb. I'm just going to I'm going to clear the my blackboard here, and let's talk about the very DE stop on FOV. All right. Now, what that simply means, is that okay. Matter of fact, let me show you here. All right. So let's get our camera back in here. Camera. Okay. Here's our ray. Here's our object. All right. Now, over in the navigator, and I'll show you here in a sec, there is a setting called FOV, Field of View. And what that does is it allows you to control the view or the field of view, the view field, all right, of that Mandelbulb environment. Now, the DE, the distance estimate, is not aware of the FOV. The field of view is not relevant to the ray marching process. However, that field of view will throw things off when the ray gets very close to the surface. If the field of view is very large, very wide, I should say, the distance estimator will essentially be thrown off. It won't be as accurate. Now, let me show you. So let's see if we can demonstrate this. All right. So okay. So I'm going to use this bulb right here. I'm going to get the navigator up and running. All right. And I'm going to walk in really, really hard. I'm really walking in hard on that particular fractal bulb. Now, obviously, everything in the scene, all right, it's the entire scene is all encompassed by the bulb because we're in so close. I'm going to send that back over to the edit. All right, let's do this. Let's set this to 3000. All right, 16:9 ratio, because I want to make that really big. I'm going to come over here and I'm going to turn this thread priority down to idle, because what happens is that, and you'll see me do this often, is that the Mandelbulb will demand so much CPU power, all right, CPU cycles, that OBS begins to struggle. All right, so I just set that to idle. I'm basically telling Mandelbulb is a lower priority than my OBS system. Okay, so let's get back over to the calculation panel. All right, what I'm going to do is I'm going to render this. All right, now I got a huge 3000 pixel wide render on a very, very close field of view of this fractal. Okay? All right, so now here's what I'm going to do. I'm going to open up this panel down here. We're going to be adjusting this field of view down here. Now currently this is at 30, a value of 30 of the FOV. I'm going to set that, I'm going to change that so that we can actually see what happens to the render as I dramatically increase the field of view. All right, so let's do this. Let's put that down to 10. All right, now that's a field of view that is extremely narrow, very narrow. Okay, I'm rendering that out. What we're going to find is that when I open that field of view really wide like that, the distance estimate gets thrown off, and it has an impact on quality. By checking on the vary DE stop on FOV setting, Mandelbulb internally will compensate for that field of view. Now let me show you. So I'm going to take this scene right here, and I'm going to get a snapshot of that. Okay, like that. Okay, park that aside for the moment. Matter of fact, let's get that bigger so that we can compare. Okay, good. Okay, so I'm going to back over to the navigator. Now I'm going to set this to 120 field of view, very wide now. Now you'll notice here that the vary DE stop on FOV is checked on. All right, send that back over to main, calculate. Now obviously I'm getting a much different scene because my field of view is very wide. And of course there's some distortion in here and everything else, but I'm just trying to show you what the vary DE stop on FOV does. Okay, so there is my render, and now let's do this. Let's take a new snapshot. All right, and I'm capturing the value. It's checked on in my snapshot. All right, now let's turn this off. Now I've unchecked. I've told Mandelbulb, don't make any compensation for FOV. The FOV is huge. The FOV is 120. It's huge, very wide. Let's calculate that. What I expect to see is that my quality has gone down because the DE stop is not accurate anymore when it approaches the surface. Now we can take a look here. All right, so this is with the vary DE stop on FOV is off, which means that Mandelbulb is not trying to compensate for that huge 120 FOV. And if I look at this, now this is when the FOV was turned on. Okay. Now let's see if we can get that a little bit closer here. There we go. Okay. Now I haven't moved the scene or anything, but you can already see how different the render is. This is the FOV turned off. This is the FOV turned on. So what Mandelbulb did here with this particular setting is it said, look, with it checked on, I'll compensate the DE stop based upon the FOV. So as the ray gets closer and closer, all right, to the surface, rather than just ignoring the fact that the camera has now been, the field of view of the camera has been opened wide up, it actually takes that into account and improves the DE stop. It is a slight modification internally to the DE stop. That's what the vary DE stop on FOV does. Now, if you may have remembered early on, when I had the FOV, matter of fact, let's try it. When I had the FOV very, very narrow, didn't really have any effect. Let's try it. All right, so now my field of view is very narrow, 10, and I'm going to get a very, very close look. You'll note here that the vary DE stop and FOV is unchecked. And you also notice that the render took longer because there's more detail in the scene. So let's grab a screenshot of that. All right. and get this where it's bigger. Just kind of plan for it to be viewed. All right, so now this is my scene with the FOV, with this particular control checked off. I'm going to check it on and re-render. Now what I expect to see here is not much difference at all in terms of the quality. Because my FOV is not huge, Mandelbulb doesn't have to make that adjustment as much when it gets closer to the surface. Okay? And I think we'll find that there isn't a whole lot of difference. I'll get my magnifier on here. All right. All right. The one to the left is with the option is turned on. The one and the screenshot here was the option turned off. Okay, so the right one is the option is turned off. Not a whole lot of difference here. There is a little bit of improvement right in here, a little bit more detail than here, but it's not as huge of a difference as was when I had the FOV set to 120. All right, so that's enough for this particular option. In summary, this option, vary DE stop on FOV, will improve your quality in situations where your FOV is very wide or wide, all right? And it's just one more little tweak for the rendering system to get your best possible quality, given, in this case, the FOV, the field of view. All right, let's clean up here. I'm gonna close Mandelbulb and I'm gonna restart it. And the reason I do that is because I want to make sure that that I'm starting because I'm demoing. I'm starting with a brand new, very, very clean surface, and I don't have to go around resetting everything. It just throw it all away and start over again. Okay. So the next thing we want to do is we want to talk about the step count on binary search. Okay. Now, first of all, I got to figure out why I'm not getting my Mandelbulb back here. It says it's starting up. It's probably on a different monitor. Probably what's going on. See if I can figure out what's going on here. Yeah, okay. All right, bear with me for a sec here. All right, let's try that again. Yeah, this is an i9 PC, pretty robust, but it got an awful lot that's going on. All right. Bear with me. We can't talk about Mandelbulb unless we get the software running. All right, this is not the fault of Mandelbulb. Yeah. What this is I got too much stuff running. I have too much stuff running on this PC here. too high a demand. Okay, now let's talk about the next option. Excuse me. All right, I'm going to get over here and get this internal set. Mandelbulb is loading. There we go. All right, I got to turn this back down to idle. I got to try to keep balance the resources of the system. All right, now let's talk about this step count on binary search. Let's go back to the blackboard. All right, and put my camera in here. All right, shoot my array out. There's my Mandelbulb object. All right, now, you know all about the steps, okay? And you know that there is there's calculations that are going on, all right, internally, and it is actually keeping track of how close it is getting to the Mandelbulb surface, all right? Now, there comes a point, I don't know, let's just say at this point right here, whatever that means. Internally, the mathematics of Mandelbulb says we're getting close. We're getting real close to the fractal surface, and we need to slow down the stepping. We need to slow it down, because if we keep going like this with these big steps, we're going to shoot right past it, and we're going to be out here and we're going to completely miss the surface of the Mandelbulb object, and we're going to wind up rendering a pixel inside the Mandelbulb object, which, whatever that might mean, it's either very detailed, wonderful, pretty, or completely black, or whatever. Okay, so we don't want that. We don't want to overshoot. We do not want to overshoot. We want to get to the surface, and we want to get to the surface and we say, look, when you hit that surface, there's something I need you to do. I need you to fine-tune where that surface is. Fine-tune it, right in, we're talking about right in here. All right, so let's clean up, come on. Let's clean up a bit here. All right, let's get my my fractal back in. Okay, the ray, okay. When it gets right in here, it's going to say, I am so close to the surface, and I hit the surface. So we got to hit. Now, the step count for binary search, what it means is this, that it will say, I need to search, I just made a hit now, and I need to search for that that surface, and I need to do it very carefully. And I'm going to, let's go back over to Mandelbulb here, right here, and I could say to the system, I'll give you 8 steps. When you get really close to that fractal surface and you hit, I'm going to give you 8 shots at finding where that surface is. It's searching. It's doing a search. All right, and I'm saying I'll give you eight little steps that you can search back and forth to find that precisely where that fractal surface is. All right, or I could give it no steps whatsoever. Let's demonstrate it. Okay. Probably the best way to do this is to get an amazing box up and running here. Let's just let's set that. Let's get that calculated. And I'm going to all right. I just wanted one formula there. Let's try that. Okay. There's my amazing box. Now let's get a whopping 3,000 on there. Render that. All right. So we're demonstrating here the step count for binary search. It's what happens when Mandelbulb hits the surface and then says, where is that surface? Where is it? If I give it no steps whatsoever, I'm basically telling it, don't engage that particular option. No, don't engage that at all. So with a 0, this is what I get for this particular render. All right, and it's at 3,000 dpi. I'm sorry, pixels per inch. And that happens to mean by DE stop. I don't care about these other values right now. I'm going to demonstrate these. So let's get a screenshot of this so that we can reference back. And now what I'm going to do is I'm going to set that up to 8. Oh, I could see how far I can go. I can go pretty high. Wow. Now that there, 30, I just basically said that when you get a hit, I'm going to give you 30 different steps back and forth that you can do to find that surface. That is too much. We don't need that. Every time it's going to take longer to render every time we do that. You get into an animation and you start doing that kind of stuff, the ultra detail on the rendering, you're adding an awful lot of time to your rendering process. We don't need 30. Matter of fact, the pop-up says 12 is more than 12 is really needed. All right, so let's be reasonable here. Let's just, so 8, okay? So let's render that. All right. So we have a hit, and we're saying you go ahead and you can use 8 different attempts, all right, to find that, to fine-tune that surface. So let's see what we got here. So this screenshot was a step count for binary search of 0. All right, and now I just did 8. Let's see what we got. All right. So it's a no-brainer. It's a no-brainer. You can see the right is with the step count for binary search is set to 0. The left is set to 8. You can already see the difference. So when you want to improve your Mandelbulb image, the step count for binary search can be very valuable, because what it does is it says, when I get close to that surface, give me the freedom, if you will, to do fine little checks to find out where that surface is, so that I can get you a good render. All right, now I don't have to. I don't have to do 0 or 8. I might say, let's try 4. Let's try 4. How do we get 4 in there? Yeah, up and down counter. Okay, so now let's render that. All right, so you get a hit. You got 4 little steps now that Mandelbulb can work on. Okay, so this was no steps at all. So you can see here that the quality of your rendering has much to do with the step count for binary search. Now, let me just take a second here and just remind you that all of these play a role in the rendering. There is no one that is going to be your best choice. You tweak them all as needed, all right, or not as needed. If you have, you don't need to put an 8 or a 12 in there if 4 does it. But once you understand that, for instance, what the step count for binary search is doing, once you understand that, you can envision, when you're preparing your project, you can envision that when we have a hit, I'm telling Mandelbulb, be a little bit more precise. You don't need to be crazy and do 30 of them or 50 or 10. And maybe 4 will be sufficient. You don't want to render any more than you have to. All right, and so putting a 0 in there obviously did not give us good results. All right, but putting 30 in there would have been excessive. We found that 8 works, even 4 is okay. All right, so let's let's move on. Let's talk about smooth normals. I'm going to put this back to 8. All right, we can stay with this. We can stay with this amazing box. Okay. All right. So now I'm going to do a render with smooth normals at 0. Okay. Now let's go to our blackboard here. What's a smooth normal? What's a normal? We talked about this in the previous 2. Let's take a Mandelbulb surface. Okay, we got a ray that comes in. Now the ray is going to say, I've hit, but now, okay, so I can make a pixel now, but what brightness is the pixel? What color is the pixel? All right, just because I hit the pixel, just because I hit the object, I don't have a pixel. Because if you can't see the pixel, then you don't have a pixel. Well, I should say you have a black pixel. And you'd get a black picture if we didn't have any light. So the normal is a calculation that will determine the 90 degree, let's say that's my fractal surface, okay? The normal is the vertice of 90 degrees. So if this is relative to the camera, obviously, if my light came in and hit a surface like that, okay, my normal is still going to be the 90 degrees off of the surface plane. All right, or if the surface, the ray came in and hit it like that. Okay, so let's make the normal white. So the whole idea is that the math is trying to figure out a vertex, an angle, that is 90 degrees relevant to the surface of the object. Now, the reason that it has to do this is because that is what determines lighting and shadowing and reflection and specular and various other things. That's all part of it. All right. Now, if I said to Mandelbulb, okay, that's fine, just you go ahead and give me the normals. Give me the normals. And every time the ray comes in and hits the surface, I get a normal. All right, we're good. We get a normal, no problem there. The issue is that if I relied upon a normal for every single ray hit, I probably would not get a good overall result. But if I said consider the surfaces just around the hit. Oh, let's take a Mandelbulb like this, and we're going to shoot straight in. Okay, so here's our ray coming in. All right. So we're going to get a normal out of that, whatever that normal is. Okay, but now the smooth normal says, look, consider the other hits right around that area. Consider their surface. For instance, if the Mandelbulb were very surfacey like that, and we have the ray come in, all right, the smooth normals will say, consider all the hits around that area to the number that I provided. All that does is it helps to average the calculation to obtain this 90 degrees by not relying upon just the single ray hit, but also considering the ray hits around that area. Let's see if we can demonstrate it. All right, so here's a smooth normal of 0. All right, let's render this. I'm going to put that back to maybe 4. Let's see what we get. Now, Normals are lighting. Normals are lighting. Normals are not necessarily quality. They're lighting. They're things like in here, shadows, various other things. Now, so let's capture a screenshot of this. All right, park that aside. Now I'm going to set the smooth normals to 8, which is the maximum. Recalculate. Normals are relating to light, color, shadows. They're not necessarily quality. All right, quality detail, sharpness. All right, so that was a smooth normal. Now this is probably going to be a little tough to see. Yeah, but I can pretty much see it here. This might be kind of hard to detect, depending upon how you're viewing this live stream, on what monitor. The colors. All right, you see this little banding right here? That doesn't exist over. Oh, it does. Okay, here. All right, right down in here. From what I'm seeing here is this area right here is a little bit faded out. It's not as the coloring is not as good. Maybe, I don't know, maybe you can see it here. All right, the right half of this area right in here is with the smooth normals of 0, and the other one was 8. It seems to me that the colors are a little bit richer when the smooth normals have been set to 8. And the reason for that would be because Mandelbulb is considering the other normals of the other hits right around that area. You'll use the smooth normals when you have critical coloring and lighting situations. If you have a situation where shadows are extremely important, the smooth normals may help or it may not. Just keep in mind that smooth normals are averaging the normals calculation that happens on each of the ray hits, all right? And normals are related to lighting, coloring, shadowing, not necessarily to quality. However, quality can be impacted or benefited by it. All right, let's talk about normals on DE. Now, again, normals. Now let's go back to our blackboard here. I hope I wasn't showing you all of this stuff with my blackboard turned on. I don't think so. Okay, I hope not. I'll check later, but I hope I wasn't demonstrating the screen with the blackboard on. But let's go back to let's get our Mandelbulb in place here. Let's get our ray in place. Now we're going to be talking about normals on DE. As I explained before, when the ray hits the surface, all right, what Mandelbulb tries to do is to figure out a normal, all right, a 90-degree vertex off of the angle of the fractal surface. Okay, the smooth normals will consider the other hits in that area. Okay, we got that. Normals on DE. The internal math of Mandelbulb is saying when you get a hit like that, all right, figure out the normal. Figure out the normal. Okay. But that is based only upon the dynamics of the ray itself. by enabling normals on DE, you're actually telling the internal rendering system to not only to consider the ray, the angle of the ray hitting the surface, but also to consider the distance estimation calculations that go on internally. So what you get is you get a slightly better result, not all the time, but a slightly better result. Let's see if we can demonstrate that. Let me get my smooth normals. I'm going to turn that back off again. Oh, hey. Oh, thanks for reminding me. Okay. I'm going to turn my smooth normals back off. Okay, that's turned off. All right, let's calculate that. So this normals on DE is not just relying upon the angle of the ray, but also considering the distance estimation mathematics that happen internally. So let's get a little screenshot of that. Okay. All right, we'll make that bigger while we're here. All right, so that's my render. And now I'm going to turn normal, this was normals on DE was on. I'm going to turn that off and I'm going to render again. Now remember now, normals has to do with lighting, coloring, shadowing. All right, so let's see if we can compare. All right, from what I can see here, with the normals on DE enabled, I'm not really getting a whole lot of difference in this particular scenario. Well, maybe if I see if I can, kind of hard to see. Basically, the colors appear to be richer with the normals on DE checked on. They appear to me to be richer. The gradients are softer. For instance, right here, that's kind of a gradient right here. That's a gradient right here. You see how it kind of goes from blue, well, a darker green to kind of a blue. Let's see what else we can find here. All right. Here's another kind of a gradient. See, it kind of goes from a kind of a dark, almost a gray. It seems to me that the gradients are a little bit more evened out. Okay, and actually, we're going to get to the next one. We're going to get to something very key, that your normals have an awful lot to do with how well gradients are presented, because gradients are very difficult to render. You'll notice right in here, this is with the smooth normals on DE turned on. Okay, all right, right here, you notice it's kind of bluish in this area, and then it kind of fades into a green. You see how even that is? How the gradient is very, very subtle. Well, that's what you want. You don't want a situation where you have very hard edges between your color changes over the surface. So by manipulating the controls that have something to do with normals, all right, that's the calculation of the 90 degree, all right, then you're improving your lighting. If for whatever reason your normal was miscalculated, then your lighting and your coloring is not going to be proper for this particular Mandelbulb surface at that point. Okay, you want that. So anytime that you can actually modify or tweak the normals, you're better off, especially when you have a lot of colors to deal with. All right, let's move on, and let's see. I'm going to reset, and let's see if we can get that bulb back. There it is. Okay. I'm going to get to the navigator, and I'm going to pull out here. That back. Okay. I don't need a huge render like that, not for this. All right, here we go. Okay. Matter of fact, I'm going to pull that back to the navigator. I'm going to walk out a little bit better. That should work. Okay, good. Now, let's talk about this first step random. First step random. Right now it's turned on. Now I'm going to demonstrate this, and I don't even need to explain it because you'll visually see it immediately. As I was talking about just a few minutes ago, you don't want a situation where you have your color bands. Let's say that we have a color that kind of shifts from, I don't know, blue to green, okay? All right, that color spread out over the surface of the fractal, all right, would be a gradient because it would very smoothly change from a blue to a green, all right? If you and this is all because of proper normals and proper rendering and all that kind of stuff. That's why you have your DE settings are mixed with normals settings because they all play hand in hand. A good quality render will give you good quality normals. All right. Bad normals, doesn't matter how sharp and clear your fractal is, your lighting is not going to be any good. So rendering is a fine balance between good quality of the surface and good normals. It's a combination of the two. And that's why these controls are mixed in like this, because they all play a role. Let's go back to our our diagram here. So if we had a situation where we had the blue, all right, and then suddenly we have the green, all right, that's referred to as a band. Okay, and you get some really ugly gradients when they kind of step. They step from one color to the next color to the, and they're not smooth. You don't want bad gradients unless that's what you're going for. And if you wanted to, you could make bad gradients with Mandelbulb. It's easy enough to do. All right, let's do this. Let's demonstrate this first step random, which is related to gradients. And I can demonstrate that by going over to the lighting panel and cranking this dynamic fog way up. Now you'll notice here that this fog intensity, obviously it's simulated, all right, will go from very bright and kind of gradually fade out. This is a gradient. This gradient happens to be going from white to less white to eventually no white, and then the background starts to come in. That's a gradient. Now, you know that every pixel in your Mandelbulb image has to have a ray behind it. And so let's go back over to our blackboard. All right, there's our camera. All right, here's our ray and our object. Okay, every single pixel that is in our system has to have a hit. All right, and then fine-tuned or whatever. And it also has to have a normal. All right, if what happens is, if these rays are obviously there's going to be a ray for the next point, a ray for the next point, a ray for the next point, and you get that. Okay. What happens is, if we're not careful, we're going to start getting a situation where these normal, oops, let's get, here's a normal for the next ray, here's a normal for the next ray. Now, I'm exaggerating this because I'm throwing off the normals. Each one of these whites is supposed to be a normal, a 90-degree angle off of the surface. If for whatever reason my rendering system does not give me good 90 degrees, then I'm going to get into that banding that I was just telling you about. Okay. All right, you got your blue, and then all of a sudden, you know, it hits pretty hard over to green. So let's go. All right, let's show it. So let me turn this first step random off and recalculate. Now you can see the banding that I've been talking about. And the reason that banding occurred is because the rays are so evenly, even and regular. So what the first step random is doing, and my camera, all right, there's my ray, there's my steps along the way, okay, all right, my fractal's out here somewhere, all right, and okay, and we know from previous discussions that that is a step, all right, and this next step will tend to be about the same until we start getting close to the surface. Okay, you know the whole routine. All right. Now, if I don't make any modifications to this system is so regular that I get banding because the normals aren't calculated properly. So what this first step on random does is it very slightly changes. Let's get a new ray in here. Let's get a new ray. Let's get another ray. And what it does is it very subtly changes the size of the first step. All right. You notice that, let's see, this one right here, this was our first step at some X distance. This was the next step, which was a random value at some X distance. So this was the next ray at some random value. By turning this first step random on, you greatly improve the render's ability to not be so regular and precise that it doesn't handle gradients correctly. Make sense? All right. All right, so now let's move on to the ray step here. The ray step sub DE stop. Okay. Let's go back over to our blackboard, and I bet you're getting tired of me drawing cameras and objects and everything. So we shot out our ray. All right, and we talked about the in the previous live stream, we talked about the ray step multiplier. The ray step multiplier talks about the internal size modification to the steps. All right, it modifies the stepping. This ray sub DE stop modifies the ray step, but down here. All right, as the ray gets closer and closer to the surface to detect a hit, this ray step sub DE stop actually decreases the size of the steps really close to the fractal. All right, let's see if we can demonstrate that. All right, so let's keep my bulb. I don't need all that. I don't need all that fog. Let's crank this all the way up to 3,000. Let's get a nice big render there. Okay, something like that. Okay. All right. So I want to go in even harder than that. I'm going to pull that over to the navigator. And I'm going to really, really, really go in on this fractal here. Okay, walk it over a bit. And that might actually be pretty good. Send it back to main, recalculate it. This is at a big 3,000 wide, 3,000 pixels wide. So this is big. I'm really in close. Okay. Make sure my internal is still idle. Okay. So now, let's try this with the race step sub DE stop turned off. All right, so let's go ahead and grab a screenshot of that so that we can compare. All right, might as well, while I have the window, might as well get it bigger. Not that big. It's got a mind of its own. There we go. Something like that. Okay. All right. Now, so this is with the turned off now. Okay. Let's turn it on, and let's do another render. Now, by turning it on, I'm instructing Mandelbulb to make those steps as it approaches the fractal, to make those steps even smaller than they would have normally have been. So what I should get is I should get better detail. All right, so this first one is the race step sub DE stop turned off. Let's get the magnifier up here and let's see what we got. So the right is turned off, the right is turned on. Okay. Okay, all right. Okay. You'll note here, all right, let's focus on this edge right here. This edge is kind of off in the distance. It doesn't, well, maybe that's not a good edge. All right, let's just take this edge right here. Okay, it's more to the foreground. All right, so this one right here to the right is race step sub DE stop is turned off, which means I'm telling Mandelbulb, don't, when you get to the surface like that, don't make these steps smaller in here. Just do your normal thing. All right, so let's see if we can compare. Okay. Now I'm looking at all along in here, right in here, and I'm trying to get this magnifier where we can see both at the same time. All right, the one on the left, that's with the race step sub DE stop turned on, enabled. I see here that we're actually getting kind of stair stepping, right? I'm getting little jaggies right in here, but we seem to be getting a little bit better detail right here. Let me get that magnifier back. No, actually we get less detail. So what I've done is by turning that on, I have told Mandelbulb to be so precise as it gets close to the surface, so precise that it's actually oversampling. It's actually being too precise. So that tells me that race step sub would want to be used when I have a very, very, very detailed Mandelbulb surface to deal with. In the case of this bulb, I've got an awful lot of these kind of smooth areas here. I don't have situations where I have extremely high detail. All right, maybe right in here might be extremely, oh, right in here, right in here. All right, well, let's, right in here. I wonder if it might be, all right, tell you what, let's try it. So let's get a screenshot. Now this is with the race sub DE stop turned on. I'm getting a lot of detail. Let's turn it off. Calculate. I'm focusing right in here. I want to see how the detail is being handled. Right in that little spot right there where we almost have sort of like sparkly. Okay. So let's get, this is with the option that is turned on. Okay, get my magnifier going here. The right is turned on. Okay. All right. All right. We seem to be getting more detail in the right with the option turned on than the left with the option turned off. It's not a huge difference, but there is more detail. Focus right here, right there. You see that little dark shadow, little area right there? All right, that is not as prominent as right here. All right, so what this shows is, by really looking at this very closely, what this is showing is that the race step sub DE stop is actually giving me more detail, but in this particular scenario, not a whole great lot of detail more, but more detail. When you look at the whole scene, all that little detail stuff, it adds up, all right? It adds up. You may not be able to see the detail improvements that are happening when you really drill in hard and you look at every little pixel, then you begin to see it. But when you draw out again, that's when all of these rendering things start to add up to a much better image, a much better render. Let's recap, and then we'll close this down. Basically, in the calculations panel here, you have a variety of controls that will have an impact on not only the quality of your render, but also on lighting and coloring and shadowing. That kind of puts us into the realm of the normals. All right? So we got two controls that assist you with getting proper normals for better lighting, better coloring, better shadowing. The other controls are quality related. All right? All right? And so now let's go back over to our blackboard and tie this whole thing together. All right, there's my camera. There's my fractal object. All right, and every pixel needs a ray. All right, the DE stop is basically the threshold of where that ray decides that the surface is. It's a threshold. All right, it's not necessarily a hit yet, but it's a threshold. It's oh, I'm close. All right, the higher the DE stop value, the wider the threshold is. Okay, low DE stop values, the threshold is tighter. All right, so that only tells the rendering system to begin to stop. The ray step multiplier is actually taking the ray. I'm sorry. It's actually taking the DE stop, and it's halving it. Like if you have a ray step multiplier of 0.5, then your DE stop internally is cut in half. ray step multiplier of 1, well, then there's no impact. Okay. So the ray step multiplier internally modifies the DE stop and is used to give that DE stop threshold even more precision. All right. The step width limiter says that it's not going to allow these steps along the ray to go any larger stepwise than X. All right. It just throttles back the stepping so that your stepping isn't so aggressive that you risk the ray overshooting the fractal. Okay? Moving down the list, we have the step count for binary search. That happens. This is put my fractal in. Okay, the ray hits. The step count for binary search has a role of saying, if you had 8, I'm going to give you 8 little steps back and forth so that you can fine-tune precisely where that fractal surface is. That gives you an improvement of the quality that ultimately is rendered to your screen. Moving down, the smooth normals is our fractal surface again. All right, our ray comes in like this relative to the surface, and we get a normal that is screwed up. That is ideally, that normal is 90 degrees, by which lighting, shadowing, and coloring is calculated from the vertice, the normal. The normal. You don't want bad normals. You're going to get bad coloring, bad lighting. You don't want bad normals. You want good normals. All right, moving down. Smooth normals tells the system to consider the other normals right around the vicinity of each ray. Obviously, that's going to increase rendering time because it's more mathematical calculations that have to go in. All right. All right, moving down, normals on DE. Rather than, we're getting really busy here. Let's clean up here. Rather than the normal being based entirely on the ray itself, let's get a normal in there. Okay. It also considers the DE math that's going, the distance estimation math that's going on. That will give you an improvement in the calculation of the normals. So you might have a normal like that. If you base it only on the ray, you might get something like that. All right, but if you add the additional mathematic magic, then your normals will be improved, ideally, all right, by utilizing the DE internal values. So this improves your normals, which improves your lighting, your coloring, and so on and so forth. All right. First step random. All right. All that's doing is saying that I'm going to shoot out the ray. There's multiple rays here, but I'm going to vary the step, the first step. Okay. So that I don't have such a regular marching that I get banding in my gradients, and fog is a gradient. Okay? Lastly, the ray step sub DE stop. All right, that plays a role over in this area here. Let's get my my fractal up there. The ray step sub DE stop. All right, when the hit occurs, it determines whether or not these little steps all in here are going to be made smaller. You check it on, they're made smaller. Okay. So, all right. So what we've done here is we have talked about in 3 live streams. We've talked about how to use these calculations in the calculations panel of the main editor to use them to get you good quality rendering and to get you good quality coloring, lighting, shadowing, gradients, and so on and so forth. So by leveraging these controls, you're better able to get a very good render in terms of quality and lighting and coloring than you would otherwise. And hopefully now I have saved you from doing one of two things. Either you look at this and you say, well, let's try a 2, or let's try a 3 and render it again, and try a 4 and a 5, and let's try 0.1. Or modifying the ray step multiplier and the D stop until you get something that looks good. All right, you may find that it might look good on your screen, but the pixels are still wrong. They're still wrong. And you don't know that until you really dive in hard and you begin to see there's a lot of defects and artifacts. You might have white dots all over the place, and the white dot is your fractal surface, and the ray overshot it, all right, or the ray undershot it, all right, and these could either be white. They could either be white pixels, all right, depending upon where that ray landed, or they could be black pixels. Look, I'm drawing a black pixel. Huh? Okay, so artifacts artifacts occur by bad settings, bad lighting, flat lighting, shadows that are flat, or shadows that are they don't appear natural because your normals are wrong. You're not going to get a good normal if you don't get a good hit. You're just not going to get a good. All right, if you have a bad hit, let's make this a bad hit. You're not going to get a good normal out of that because the system doesn't know where to put the normal. All right, mathematically, it doesn't understand where to put the normal. All right, so if you have a bad distance estimate ray march, okay, you're going to have a bad normal. You can't get around it. Because the normals and the quality are all based upon the distance estimated method of ray marching in the Mandelbulb. So let me leave you with this thought. If you want your best possible image, your best possible render, you need to not only understand what these are, but be able to leverage them, and kind of basically over time you'll understand where these things really play a vital role. You might have a fractal that has a lot of very mechanical, a lot of flat surfaces. Well, your settings in this area here will be slightly different than if you have something like what I have on the screen now, which is very organic, very flowing. All right. So over time, you'll be able to understand how to leverage these depending upon your fractal scene and how it's constructed in order to be able to get good renders. And you get good quality renders, you're going to get good normals. And that means you're going to get good lighting and you're going to get good coloring. All right. So I hope these three live streams combined collectively have helped you understand the Mandelbulb method of ray marching and how these various controls fit into the whole picture. And hopefully you're in a position now to take this further and understand how to get the best possible renders so that you can put a lot of work into actually building a fractal scene, and now you can actually leverage your scene to be able to get very, very good quality, high quality renders in terms of the detail, in terms of the coloring. So I hope that these 3 live streams have helped a lot. Look, get up on my Learn Mandelbulb3D channel. And you got a question, type it out and shoot it out to me. I'd be happy to see if I could answer it for you. Okay? All right. That's it. Then I'll see you on the next live screen. And you keep creating and having a good time with Mandelbulb. And I'll see you at another time. Watch my channel, because I'll announce the next live stream, and there'll be others. We got plenty to talk about. All right, I'll see you around. Take care.